and everyone loves hackers. All right, great. So, oh, transitions, right? No. So I'm Kyle Cothern. I was just wonderfully introduced by Brian, and I'll be talking about going vertical today, so vertical integration type stuff. This is something I worked on. It's a launch pad for a rocket, Falcon 9. You probably heard of it, seen it, goes to space. First off, I guess we should talk about horizontal integration. So this is the N1 moon rocket, and as you can see, they put it together horizontally, roll it out on this thing called the Grasshopper, and stand it up vertically. They flew 5 of them, they all blew up. It's pretty tragic. Then you can see we got the Falcon 9 rocket, also horizontally integrated, here at the Launch Complex 40 in Cape Canaveral. I actually worked on that little bracket up at the top, the droop tool, which no longer exists. This is a very old version of the rocket. And the biggest horizontal integration, Falcon Heavy at 39A. You can see they got a slightly larger transport erector for this one. And then, of course, the largest rocket, Saturn V, was vertically integrated, not horizontally integrated, which is, you know, the point of the talk is that vertical integration, much better than horizontal integration. This is just all a joke, though. Essentially, vertical integration is combining multiple business parts of a company into one company. So what you're trying to do is pull in manufacturing, you're trying to pull in like consumer-facing things and basically stack everything up so that you can, from raw material to output, control everything. The point of this talk is that vertical integration is an important tool that you can use in your startup, not normally by buying companies, but like setting up parts of your business that will allow you to more fluidly convert raw material into business. A lot of you guys are electrical engineers. I'm a mechanical engineer. I guess I should start out with that. I mostly design large structures, but I also occasionally do a consumer product. This is me when I was much younger and had more hair. At Cape Canaveral, in the hangar with Falcon 9, we were integrating that rocket to that transport erector. One of the things that I was sort of thrust into was SpaceX, which is an incredibly vertically integrated company. They convert aluminum and steel into pretty much everything that they need to launch stuff into space. And it's quite amazing to have walked into that after getting out of college, when you can sort of just make a drawing and suddenly there's 30 guys welding up your frame at the highest levels of performance. So that was kind of where I got started in engineering. Then I went on to Hyperloop One, which this is a picture of me and Jake on top of a Latorno log stacker, which is a forklift used for loading log mills with logs, but we happened to be putting a Hyperloop tube on some dirt piles because we were practicing. I'm flying a drone, taking a selfie. It's over the top. Basically we tried to figure out everything on our own for Hyperloop, like in a lot of ways, because most of Hyperloop is building a large tube between 2 cities, and not a lot of companies do that like in a vacuum setting with like a high-speed vehicle traveling inside of it. So the tolerances are weird compared to everybody else, and the supply chain is weird. You can kind of go to pipeline manufacturers, but they don't know when cylindricity is, which is really hard because you're trying to make a cylinder, and that's the tolerance that you use for that. So we tried to stack vertically as much as we could inside the company, and I did a lot of that. Most of my role was designing the structure, but also setting up the manufacturing capability engineering process. So that was kind of my philosophy at that company, and that's kind of why we got to the development system that we did in the amount of time that we did, about 1.5 years. That kind of, now that you have some background on me, so this is what we built with it. Obviously, it's a 500-meter long vacuum tube. It's the 3rd largest vacuum system in the world as it stands. The vehicle in it goes about 250 miles an hour. It was supposed to be 7 kilometers long, but startups, I'll say that. It's quite impressive that we managed to get it built in the amount of time we did, and it allowed us to learn a lot. And I think that's one of the biggest things you get from building stuff in-house, is that you learn everything that you would normally give to a contractor to learn, and then you can ask them to document it and send you that documentation, but they don't really. Communication between companies is much more burdensome than a lot of people want to spend time doing, and so you end up normally just losing a lot of that information, tooling, best practice that is developed by a contractor. I kind of want to narrow the scope of this talk to hardware startups that are doing things that aren't mostly like appliance or branded object. So I just went ahead and picked an example of something that this talk is like not specifically about. If you're building something like Treau, you shouldn't vertically integrate. And here's why. There's a ton of people who can build that for you. Also, don't design anything like that. It's really complicated for something you do with your hand. But I'll get back to that later. Kind of the things you need to think about when you're starting a hardware startup are paying attention to detail, like in what it is that you're designing, trying to apply creativity to whatever your problem is that you've noticed, good logical thinking. I know that's like a stretch, but a lot of times you'll find that like people didn't really think through the whole idea. They just kind of got it and then went with it before they realized that maybe it doesn't really work out if you think about it. Once you've sort of come up with a logical reason to get into a design, you need to do a lot of research to understand what the state of the art is, what the best practices are, and what the first principles are that you're trying to design from. From there, you should really go down the theory road and apply that theory in order to come to whatever your design is, execute on it, verify that you properly executed on it. And those are kind of the things you do in a hardware startup. Whether it's for electronics or a medical device or a rocket engine, you really have to be critically thinking about what you're doing. And vertical integration is the obvious conclusion if you think, oh, I would like to build the best possible product, because really you're crunching all of that process into one place, and so the communication is very tight and very quick. So the kind of hardware startups I am talking about, and the ones that you'll find have at least vertically integrated in terms of their hardware prototyping phases, are like Tesla, SpaceX, Apple. There's a company down in LA called Divergent that makes 3D printed cars. They've got all their 3D printers in-house. The Boring Company, they're building their own TBMs. Zoox is building cars. They've got a shop. Z-Aero, they've got a pretty sweet little aerospace shop down there in, where are they? I guess they're in the valley. And then Relativity is another launch startup. There's about 10 rocket startups right now, and most of them, while they're farming out parts here and there, are doing like the core work inside, and that's because it allows their engineers to work a lot faster. So here's my this is my hockey stick chart. I didn't spend a lot of time on graphics or money. So this is your startup, right? You start with nothing down at the bottom left, and over time you attempt to make a hockey stick, and they don't grow on trees unless they're wood. Small businesses tend to do this lower line here. So when you're trying to move up that very steep curve, your burn rate, your number of employees, your complexity, how much money you're trying to raise, the amount of pamplemousse LaCroix you're drinking, cost to change design, sweat, blood, and tears just goes up and up and up. And when you're trying to get up this curve, one of the things that really sucks is when you have to wait a week for something to happen, right? Or 2 weeks, or there's a serial operation so that a project that requires 3 or 4 things to come together gets bumped and bumped and bumped and slips out, right? And so really trying to eliminate those difficulties in making your way through the design cycle over and over is what you're trying to build at the company. You're trying to build a team and a process that allows you to move up this curve as quickly as you can, right? So I guess the first story is like, all right, what are you going to build? So at SpaceX, we're building a rocket. The common dome is backwards. Ignore that. So a rocket is basically a tube, in case you weren't aware. You've got your liquid oxygen on the top, you've got your RP1 in the middle, and you've got your engines on the bottom. And all that stuff goes down through the engines and provides thrust and sends you to space, or it blows up and you fail. So you have to make all of this stuff or buy it. You got to make COPVs, cold gas thrusters, control surfaces, the list goes on. And it costs a ton of money to make rocket engines. It doesn't cost a ton of money to make this graphic. It was very fast. So one of the big things that SpaceX tried to do first was go buy rockets. So Elon went to Russia and attempted to buy an ICBM from the Russians. Now, if you know anything about buying rockets from the Russians, it's totally possible and doable. I think, Orbital, no, Space, I forget the name of them. One of the other big rocket companies, sorry, I'm blanking on it right now. Orbital Sciences buys, another company imports RD-180s and then converts them so that they can use them on their orbital launch vehicle, Antares. But you run into a lot of problems when you do stuff like that. Namely, their rocket blew up and landed on their pad and blew up most of their pad. But you have quality issues. You don't really know what's in there because all those RD-180s have been sitting in a hangar in Russia for the last 70 years. And you bring them in, and the insides of them are made of some weird unobtainium that the Russians developed during the space race, and you don't really know what it is, but it's great stuff, but you can't replicate it, so you can't build any more of them, right? So it's really hard to buy off-the-shelf parts when you're trying to do something like this, right? So SpaceX, they had problems going to vendors and just getting parts made. Once they decided that buying an ICBM wasn't going to work, I think Elon got spit on. That's the story. I wasn't there. But you run into a lot of problems with vendors. You go out and you try and get a little aerospace startup in Mojave to make some parts for you. They come back, they don't really work. Now you're stuck because you were supposed to launch in 6 months, and that thing that was supposed to generate all the gas for your engines is not generating gas. And so you have to then figure out how to get someone else to make it, but there isn't anyone else to make it. So at that point, you start buying machines and trying to do it yourself. So there were multiple kind of concurrent problems at SpaceX. This is a picture of them once they made it. This is actually at Vandenberg. It's a launch. Long exposure. It's pretty cool. So once you finally make it, and I'll play this in a minute. Once you finally make it to finally building a rocket, right? You did it. You built a rocket. Now you have to build a lot of rockets. You don't just get to build one. Unfortunately, you have to build many. And all those problems you had with vendors just to build that first rocket now exist at scale, right? So if you can't outsource fast enough and you're sitting in lines with ULA and Boeing and every other aerospace manufacturer to get your parts made, then all those employees that you hired to design your rocket are sitting there waiting for the parts to come back, not learning whether or not their parts work, right? And that's something that happens at a lot of startups is you finish your design, you send out your parts to get made, and you're sitting there waiting around for your parts to come back. And you can try and stagger the design process in order to kind of mitigate that. But at the end of the day, the faster you can put stuff out, the faster you can learn, the faster you can make the better designs and start beating everyone else. And so this is a compilation of what happens when you build rockets very quickly. So they blow up, which is great. It's very entertaining. So this is a compilation that SpaceX put together that's pretty great. Ever since they started launching rockets, they've been trying to land them. Because as it turns out, when you launch a rocket, you're putting $100 million worth of stuff up in the sky. And if you don't get it back, it's very expensive. So SpaceX figured that they could get it back. And so they started building rockets as fast as they could to try to land them. Because you can't really simulate what happens when a rocket launch happens down to the T to be able to figure out how to land it. And they ran into all sorts of esoteric problems that you would never anticipate when you start designing a rocket. So this is like a really great montage, but I'm actually going to skip out of it if I can really quick here. Oh, and I have no idea how to skip. Maybe? Nope, that's just slowly fast forwarding. Yeah, there's a lot of rockets that they blew up. Nope, now it's, nope. Okay, we're going to escape out and skip slides manually. Hold on, guys. So again, this is like a draft presentation. All right, cool. Is it going to, don't start from the beginning. All right, great. So you're not actually building a rocket. You're building this. You're building a rocket factory, right? You're trying to turn raw materials into orbital boosters, because if you can do that quickly and cheaply, then you can learn new things that other people who don't have access to those tools and can iterate that quickly can learn, and you can beat out the market, right? So this is SpaceX in 2002. There's a McLaren F1, which is a great car, and there is an empty factory. They actually got a Bridgeport first, which is primo choice. One thing they didn't get was a big enough door. Falcon 1 was designed around the size of door in this building. That is why it is the diameter it is, which is silly. But yeah, when you start out at a startup, you don't really have a lot of capital resources, but if you gradually phase in building out capability, it empowers your engineers to really make it down the road fast in terms of like turning parts around. So what SpaceX did was they bought a lot of stuff. So this is SpaceX Hawthorne in 2008. It's like 5 years later. At this point, SpaceX has transitioned from Falcon 1 to Falcon 9. And if you notice, there's a dragon in the background here, the pressure vessel. But it's still very rudimentary. They're just, I mean, they built all their tooling in-house, like all these little bridges and things, and like all those integration rails. All that stuff got built in-house by a team that they hired from a company called CFI, which was Bob Reagan's machine shop in LA. And as it turns out, the way they kind of figured out how to do that was they actually did what is classic vertical integration. They were going to Bob Reagan to build parts in his shop because he was one of the better fabricator shops in LA. And they were having to wait in line, and they got tired of waiting in line because it was costing them more money to wait in line than that shop operated in terms of their like yearly revenue. So they basically said, okay, great, how much money do you want? Come work for us. And they basically picked up Bob Reagan's shop and set it down outside next to SpaceX and then built a building around it. And that is the SpaceX machine shop now. So they kind of took vertical integration to an extreme because basically it was all to skip the line for this particular rocket build. But they've continued. So this is in 2013. You can see that they've gone from building just barely one Falcon 9. And I think that was either Flight 1 or Flight 2 in that picture. Oh, by the way, let me just skip back really quick. This picture and many more like it are on Steve Jerviston's Flickr. Steve Jerviston is an electrical engineer VC that has an amazing Flickr. He sneaks into all the places where you're not supposed to go and take pictures, takes pictures, and posts them on his Flickr. So if you want to see like the back room of SpaceX, check out Steve's Flickr. Now they're making 40 cores a year in 2013, or they're trying to anyway. In this picture, you see 2 second stages, 3 first stages, which is basically a Falcon Heavy and a half. And you can see that like there's all sorts of stuff going on over here. There's like internal buildings inside the warehouse. This is the same warehouse in the last picture, by the way. So really, they scaled up very quickly, and they purchased the capital equipment in order to empower the engineers to go down the road very quickly and build rockets. So this is kind of a rough transition. This is a junior engineer, actually it's an intern, that worked for me at Hyperloop. And it's her very first day driving a telehandler. Also, what you can't see in this picture is there's an $80,000 tube sitting up here that you can't see, that she drove this thing off-road, turned around, and lifted the forks up to the tube to check whether or not an integration tool would work. So one of the things I want to kind of touch on here is a lot of the reasons startups don't vertically integrate is because it's scary and it's expensive, right? One of the things that you as engineers probably have encountered is a little thing called learned helplessness. So basically, if you get told not to enough times, you assume that that is no longer on the table, right? One of the great things that I've learned over the course of working for both Elon and at Hyperloop is that nothing is really off the table. Just ask a little harder. And what we were able to do at both of those companies is sort of buck tradition, say throw caution to the wind and try things that may have been tried before or were against industry convention, and occasionally we would get lucky. So kind of opening up your risk stance and going after things like buying a machine that you don't even know how to run and figuring out how to run it can totally be worth it and pay off in the end. So kind of, oh yeah, anything is possible. Zombocom. If you aren't familiar, it's a great website. If I can, hold on, just, oh no, sorry. The only limit is yourself. So one of the things kind of that I wanted to get at here is every time you build something internally, it kind of gives you this ability to directly set your critical path and influence the people who contribute to that, right? So a lot of times when you go outside and buy things, you're paying vendor margins, you're in their like priority stack, and they don't have your best interest in mind because whether your company succeeds or fails is really not material to them. They just want your money, right? So if you've got a machine shop in-house where you can go and spend the time to work with the machinists or to work with the people doing technical fab of your product, you can often get benefits in both directions for both engineering and like final quality of your product. So this is a good example of what happens when you try and bring stuff inside. So kind of bringing stuff in-house is something we did when we built the development system for Hyperloop. And so the goal here was not necessarily to build all Hyperloops in a shop. It was to set up a fabrication capability that would allow us to prove out whether or not it was possible to even build a vacuum train at scale in the cost margins we were thinking, but also to then go and build the tooling to build the next one. So one of the things you should always be considering when you're setting up any fabrication capability is what that is going to be used for after the prototyping phase that you're in. And generally that should be used to grow your capability further. So basically what we were building here was the first set of tubes and then specialized tooling for building the next set of tubes for Hyperloop. So kind of we did design of the Hyperloop, and I think this is a great point earlier not to do DFM until after you've done your design. So we were most of the way through the design, and we identified the need to potentially set up a manufacturing capability, at which point we looked at our project schedule, which is something that you will find yourself doing quite frequently, and we looked at how long it would take us to farm out all the parts, and then we did a quick study of how long it would take us to set up a manufacturing capability in-house. We figured it would probably take about 6 months to stand this up and cost about $4 million. So the project budget was like $100 million. So roughly one Falcon 9 rocket in terms of cost, as sold, not as not as built. They build them cheaper than that, or else they wouldn't be making any money. So we figured for about 5% of the overall project cost, we could reasonably build the capability to fabricate everything. To be fair, we didn't fabricate everything. We farmed out the tubes themselves because that's a pretty major investment to go buy a spiral pipe mill. But we did investigate that, and it turns out that this is very possible, but there's only one company in Turkey that makes them, and their lead times are extremely long. We were going to design one in-house, but we didn't have enough resources. So essentially, what we set up here was a fabrication shop. And so kind of what you want to do is you want to think, how am I going to process my raw material? How am I then going to do any 2D or 3D operations to make that into parts? And then how am I going to go and assemble those parts into a made thing? So for a PCB, for example, you would want to figure out how you're going to do your board fab, how you're going to get your ICs, how you're going to get all your components, and then how you're going to do all of the pick and place and assembly and testing and on and on. And so for this specific case, we sort of laid everything out, weighed it against our other options, and decided to go for it. And so kind of some of the things we had set up here were we had saws and iron workers. So here's a saw for cutting material down when it came in. Then we had a water jet. Well, we had 2 water jets that we used for 2D cutting of parts. We had some CNC machines. This is a 20 by 40 mill. These are for basically taking billet material and turning it into components. We had a couple production lines for modifying the tubes that we set up that were basically like, tube goes in one end, comes out the other with all the extra parts on it. This is an example of what's going on in one of those tents. So they're trimming the tubes to the final length. And then we also had some specialized tooling. This is called a circular mill that we went out and had like custom fabricated so that we could do things like field joints and stuff like that where we needed precision machining. So basically we sort of powwowed with engineering and figured out what types of capabilities they might need. They hadn't quite finished the detailed design yet. And that's key. You really want to get in there if you're working on a really big project before it's too late to actually go and get everything ready and set it up. Because what happens is when you step into the project itself, something like building a rocket or building a Hyperloop, you really want to kind of have all that capability ready to go. Because what will oftentimes happen is you had a great design for a braking system, and it had some really tight tolerances, and you bought everything to hit those tolerances, but then at the very last minute, you went and built it and tested it and figured out that it really doesn't work, and it actually breaks and explodes when you try and use it. So what you do is you say, we've got this huge shop with all these tools in it. What else could we do, right? And you can very quickly turn a new design around. Whereas if you sort of had something that you're waiting to get from a vendor to prove out, right? And you're waiting and waiting and waiting, and finally it gets delivered like right towards the end of the schedule, you don't have that internal capability to say, oh, this doesn't work. And basically the whole project is slipping and the whole company is pushing out to when you can raise the next round, right? So one thing that's unique about this situation that separates it from what you would want to do in a small business is you're burning at both ends, right? Like you want to spend as much money as you can, to do as much as you can, to raise as much as you can in the next round, and you want to do it all before the next round. And so if your schedule slips, you could push out and miss the round basically and have a down round, or potentially your company might fail. In the other direction, if you don't spend enough money, you might not raise as much money as you could to be able to go and then have the impact that you want to have in the world. So here's field installation. So that was kind of the trailing end of the stack that we built up for building this system. And then you've got QA. So this is a guy out there with a laser tracker. So we established a metrology team in-house that could go out and do the precision measurement to verify what we had built. And one of the things, we were actually using contractors to do this as well, but we would actually send our guys to check their guys, because you can build trust with an internal team, but it's much harder sometimes to build trust with vendors, especially ones that aren't always available when you need them. So even if you don't build an entire vertical stack for your company to build your product, maybe even at scale, if you even build a small part of that, you can use that as a litmus test against vendors when you go to evaluate them, when you have internal experts. When you have no internal expertise, it's a lot harder to figure out what's happening. In conclusion, go out there and make stuff. Like that's really how you learn and where you learn to decide whether or not you're going to vertically integrate or what you're going to bring into your company. It's oftentimes a trade against how much you think it will return and how much you think it'll expand your capability or allow you to commit your vision to reality. But I do think that like the real value of doing it is that you get all this knowledge that you wouldn't have had before. So here's my shameless plug slide. I'm Kyle on Twitter. There's my website. Go check out Crashbase in LA if you're ever down there. It's a cool hacker space where there are lots of interesting, nerdy people working on cool projects. And this is my last slide. So thanks for your time.
So crypto means cryptography. What? Yeah. So.